In a parking lot in Michigan, a car pulled up to a charger with 4% battery left. 90 seconds later, it pulled away at 80%. No one in the crowd clapped. They just stood there doing the math, because that number should not be physically possible with the batteries America has been building for the last decade. For 15 years, every serious conversation about electric cars ran into the same wall. Charging takes time. Not minutes you can ignore. 20, 30, 45 minutes standing at a plug while your coffee goes cold. Automakers called it range anxiety and spent billions trying to design around the problem instead of solving it. Bigger batteries, more charging stations, software that predicts when you'll need a charge before you do. China built the largest fast-charging network on Earth to paper over the same wall everyone else was hitting. Nobody actually fixed the chemistry underneath it. If you're getting something out of this video, hit the like button. These take real time to research and put together. And subscribe so you don't miss the next one, because what happened next in a lab outside Detroit is the kind of thing that doesn't get believed the first time you hear it. To understand why this matters, you have to understand what's actually slow about charging a battery. Because it's not the plug, and it's not the charger. It's one specific part inside the cell. When a battery charges, lithium ions move from the cathode across to the anode, and in almost every lithium-ion battery on the road today, that anode is made of graphite. Graphite has a speed limit built into its structure. Push ions into it too fast, and instead of soaking in evenly, the lithium plates onto the surface like frost forming on a window. That plating is exactly what causes battery fires. So for 15 years, every automaker on Earth throttled charging speed on purpose, not because the electronics couldn't handle more power, but because the graphite couldn't. That speed limit is the real reason your phone and your car both charge slowly. It was never really about how much power a charger could deliver. It was about one material inside the battery that hadn't changed in any meaningful way since the 1990s. The company behind this breakthrough is a battery materials startup working with a Michigan-based automotive supplier. And the fix isn't a new kind of battery chemistry at all. It's a new anode. They replaced graphite with a silicon-dominant structure engineered in a lattice pattern. Picture the difference between a sponge that just soaks up water shapelessly and a set of shelves built specifically to hold something without the whole structure collapsing. Silicon alone can theoretically hold up to 10 times more lithium than graphite, which is exactly why engineers have chased it for 20 years. The problem was always that pure silicon swells by as much as 300% as it charges, and cracks apart after a few hundred cycles, which is why nobody used it at scale before, no matter how promising it looked in a lab. This version solves that by binding the silicon particles inside a flexible carbon framework, something closer to a cage than a cage that lets the silicon expand and contract inside it without breaking the connections around it. It sounds like a small engineering trick. It is the reason this battery can charge at a speed graphite anodes were never physically capable of. The lab results, independently verified by a third-party battery testing group, showed a full 10% to 80% charge in under 90 seconds on a pack sized for a compact SUV. That is roughly the time it takes to scan a gallon of milk at self-checkout. The cells also survived over 200 full charge cycles at that speed with less than 8% capacity loss, a number automakers consider production viable, not a lab curiosity that falls apart the moment you try to manufacture it at scale. Here's the part that made this real instead of theoretical. A major American automaker signed a supply agreement in the spring of 2026 to integrate the technology into a next-generation electric truck platform, with pilot production lines already being tooled at a plant in Ohio. This isn't a concept demo on a stage under stage lighting. It's a purchase order with a delivery date attached to it. And pilot lines don't get tooled for something that might not ship. A second American automaker followed within months, this one targeting a compact SUV platform aimed at a lower price point, betting that fast charge capability could become the deciding factor for buyers cross-shopping gas and electric for the first time. Two separate production commitments on two different vehicle segments, inside the same calendar year. That is not how automakers behave around unproven technology. Automakers are famously conservative. They test for years before committing a single dollar to retooling a plant. Two commitments this close together is the industry equivalent of standing up in a meeting and admitting the other approach isn't working. China's response is the most telling part of the whole story. Chinese battery manufacturers, who currently supply the overwhelming majority of the world's EV battery cells, have spent the past 2 years racing to commercialize silicon-anode chemistry themselves and have publicly struggled with the exact same swelling problem this American approach solved. Industry analysts tracking Chinese battery patent filings noted a sharp increase in silicon-anode applications within weeks of the American test results becoming public, the fastest documented reaction time in the battery industry in recent memory. When a country that controls most of the global supply chain suddenly accelerates research into a technology it wasn't prioritizing a year earlier, that's not curiosity, that's catching up. It's worth pausing here to talk about why this matters beyond bragging rights. Whoever controls the anode material controls the cost of every electric vehicle built on it. And right now, that control sits almost entirely overseas. An American-developed anode that can be manufactured domestically using a Michigan supply chain instead of processed material shipped from across the Pacific changes more than charging speed. It changes who sets the price. And it changes what happens to that price if a shipping lane ever gets disrupted or a trade relationship ever sours. Now, the honest limitation, and it's a real one. 90 seconds is the lab number, under ideal conditions, with an ideal charger delivering far more power than a normal home outlet, or even most public stations can currently provide. Public charging infrastructure in America is nowhere near ready to deliver that kind of output to a parking lot full of cars simultaneously. The grid connection alone for one of these ultra-fast stalls needs roughly the same power draw as 40 homes running at once. Multiply that by a full row of chargers at a busy highway stop, and you're talking about power infrastructure closer to a small industrial facility than a gas station. The battery is ready. The charging network isn't, not yet. And building that out is a slower, less glamorous problem than inventing a new material. It involves utility companies, permitting, transformer upgrades, and years of construction, the unsexy infrastructure work that never makes it into a headline the way a 90-second charge does. Analysts estimate a meaningful national rollout of chargers capable of delivering this kind of power is realistically 5 to 7 years out, even with the battery itself ready today. There's also a cost question nobody has fully answered yet. Silicon-dominant anodes are currently more expensive to manufacture than graphite, largely because the carbon framework that keeps the silicon from cracking apart is a precision manufacturing process, not a bulk commodity process. Early production vehicles using this battery are expected to carry a price premium over comparable graphite anode models, at least for the first several years, until manufacturing scale brings the cost down the way it did for lithium-ion batteries themselves 15 years ago. And there's a durability question that only time will answer honestly. 1,200 cycles in a lab is roughly 4 years of daily charging for an average driver, which sounds solid, but it's still a controlled test, not a decade of real driveways, real winters, and real drivers who don't treat their car the way a lab technician does. The company has stated it expects real-world performance to track closely with lab results, but expects is doing some work in that sentence, and nobody will know for certain until the first production vehicles have been on the road for several years. Still, put the two facts next to each other. 15 years of automakers designing around a charging problem instead of fixing it, and a small team outside Detroit that looked at the actual bottleneck, one material inside the battery that hadn't fundamentally changed since before most current EV engineers were born, and rebuilt it from the inside out. That's a different kind of breakthrough than a bigger battery pack or a faster charger. It's the kind that doesn't need the rest of the world to catch up to it. It needs the rest of the world's chargers to catch up to it, which is a much shorter list of problems to solve. Think about what this actually changes for a normal driver, not an engineer, not an analyst. Right now, a road trip in an electric vehicle means planning around charging stops, checking an app, picking a route based on where fast chargers exist. A 90-second charge, once the infrastructure exists to deliver it, turns an EV road trip into something closer to a gas car trip. You pull off, you wait about as long as it takes to use the restroom and grab a coffee, and you're back on the highway. That's not a minor improvement. That's the single biggest psychological barrier to EV adoption in America, solved by a material scientist's decision about how to shape a cage of carbon around grains of silicon. But here's the number that closes the loop, the one that started this whole video. That car in the Michigan parking lot went from 4% to 80% faster than it takes most people to pay for gas and walk back to their car. The chemistry problem that automakers spent 15 years designing around instead of fixing just got solved in a lab outside Detroit. 2 American automakers have already put purchase orders behind it, and the country that controls most of the world's battery supply chain is now racing, patent filing by patent filing, to catch up to a fix America already has tooling built for. The charging network isn't ready yet. The cost premium hasn't come down yet. Nobody has driven one of these packs for a full decade to prove the durability holds. But the hardest part, the part every automaker on Earth assumed was simply a law of physics you had to design around, just turned out to be a design choice all along. And once you know a wall was never load-bearing, it doesn't stay standing very long. If you enjoyed this, hit the like button, subscribe, and turn on notifications so you don't miss the next one. There are related videos on the screen right now if you want to keep watching. So here's a question for you. Would you actually trust a 90-second charge with your car's battery long-term? Or does that speed make you nervous about what it's doing to the cells underneath? And do you think the charging network catches up in 5 years? Or does the infrastructure end up being the real bottleneck for another decade? Let me know in the comments.